Welcome to Notes 84, Essential Skill H4, converting between polar and rectangular coordinates. Rectangular coordinates are simply x, y coordinates. We also call these Cartesian. To start, we look at where these came from. Cosine of theta is defined as x over r. Sine of theta is defined as y over r. When we solve for x and y, we get a conversion formula. For example, if we know r and theta, such as 4 and 45 degrees, we can convert coordinates between polar and rectangular. 4, 45 degrees is here. To convert, we simply plug into these formulas. And so our final answer, in ordered pair form, is this. In our second example, we have a radian angle, and we'll use the same technique. Feel free to pause and try it yourself if you like. Our next task is to go the other way. I'll give you rectangular coordinates, and we'll figure out r and theta. We start by looking at the equations that relate r, x, y, and theta. Since we're looking for an angle, we need to know which quadrant it's in. We can get that from the coordinates of the xy point that we're given. For example, we want to plot this xy point and convert to polar coordinates using the formulas above. To find theta, we need to go through the tangent function. Our final answer is r comma theta. Here's another example. In quadrant 3, we're going to have to estimate the radical value. The square root of 3 is approximately 1.732. Notice that even though x and y are both negative, we get positive angle and positive r. We can adapt this technique to convert equations between rectangular and polar forms. We'll use the same formulas for conversion. Converting equations can require a bit more creative problem solving. We look for opportunities for substitution and use them. In this case, r equals plus or minus 4 simply describes a circle. The important thing to realize is that we can simplify this to r equals 4. The reason is that theta can do whatever it wants. If theta is 0, we could plot r equals negative 4. If theta is pi over 2, we could plot r equals negative 4. We would end up with exactly the same circle that we would get if r were positive 4, and we simply looped through the angles. This works with circles. It doesn't work with every equation. To convert a line, we simply convert x to r cosine theta, then solve for r. The majority of the time, we're going to have equations that are solved for r as functions of theta. The only variables allowed are r and theta. Let's look at a vertical line. Now we look at a hyperbola. X squared minus y squared equals 9. it's tempting to try to use somehow x squared plus y squared equals r. You can see we run into problems when we try to get that sign to change. Instead, we'll fall back on r cosine theta and r sine theta. From here, we need to solve for r squared. Then we can take the square root if we need to. To do that, notice that we can factor r squared out. Now notice that we have an identity that we can make a substitution for. This will help us simplify. For our final answer, we simply take the square root of both sides. Next, we look at a parabola. Our only substitution that seems to be available is r sine theta and r cosine theta. At this point, the easiest thing to do is to simply divide both sides by r. And we use identities to simplify. And we're done. For our final rectangular equation, we look at a sideways parabola. Again, we can use identities to simplify. Our final task is to go the other way and convert polar equations back to rectangular. This can be somewhat more difficult because we're trying to create expressions. We can't just substitute for single variables. We want expressions like r sine theta, r cosine theta, r squared would be nice. And then we can substitute something simpler. In this case, there's nothing obvious, so we make a substitution first. So this polar equation is simply a straight line. Our next example is a little bit tricky. We have sine of theta on the right or on the left. What that means is that getting r sine theta out of this is not going to be possible. If we divide both sides by sine of theta, we don't get something useful. Instead, our strategy is going to refer back to these parabolas. Specifically, we divided by r on both sides. In this case, we're going to go the other way. We're going to multiply by r on both sides. Now we have some substitutions we can make. R squared is convenient, and so is r sine theta. Next, we need to get this into standard form for whatever this is. We have two squared terms, and so we know from our work with conics that this is going to be a circle, since both squared terms have the same coefficient. To get it into standard form, we subtract the 4y term over, complete the square, and finish up the standard. And so this polar equation is actually a circle with a center of 0, 2 and a radius of 2. Our final example isn't solved for r at all. In fact, r does not appear in this equation. What that means is that r is free to do what it wants, and all we have is an angle that limits it. This is best visualized on a graph to see what's happening. We have an angle at pi over 3, and r can do what it wants. Remember that r can also be negative. So our expectation is that this will be a line. Now, how do we solve this algebraically? Well, we know that tangent of theta is something we can replace. So we're going to take the tangent of both sides. This is simply a straight line with a slope of positive square root of 3, which matches our estimated diagram. Thank you for watching.